Hello everyone. This is section 10.2, the chi-square test for independence. So we have a Greek letter, looks like an X, it's a fancy X, and that's the Greek letter chi. So that's how it's pronounced. And recall that we say that two events are independent if the occurrence of one does not affect the probability of the occurrence of the other. And we're going to be looking at the critical value method for performing what is referred to as a chi-square test for independence. And the critical value is going to be denoted by chi-square sub 0 and the test statistic by just chi-square. So we have our critical value, just like we did z sub 0 and z, or t sub 0 and t, for the critical value and the test statistic, respectively. So again, it's chi-square. So example 1a says, suppose a researcher claims that achieving a basic skill level in a subject is related to the location of the school. And to test this claim, we can determine if the skill level achieved in a subject is independent of the location of the school. So what we do is we form what's called a contingency table. So R stands for rows and C stands for columns. And we have what we refer to as observed frequencies. So those are the frequencies that are tabulated from your little survey or questionnaire. And each one of these entries represents a cell. So the intersection of a row with a column is referred to as a cell. So there's what we call a 2x3, 2 rows, 3 columns, contingency table, showing the observed frequencies for that situation. What you always want to do is sum the rows and sum the columns. So if we add 43 and 63, we get 106, 42 and 66, 108, and 38 and 65, 103. So those are the sum of the columns, sum the rows, and adding those three numbers we get 123, and the second row 194. And then this number in the corner here represents either the sum of the rows or the sum of the columns. And that's your grand total. And in this case, 317. So that's the total number of entries, or of pieces of data observed. And so we have what we call the expected frequency. And it's denoted by E with a subscript of R and comma C. So that's given to be, depending on where the cell lies, it's the sum of the row times the sum of the column divided by the sample size, or the total. So here we want to find the expected frequencies for our given table. So E sub 1, that is the expected frequency of the cell in the first row and the first column, is going to be the row sum, 123 in this case, multiplied by the sum of the column, 106, divided by the grand total, 317. And if we crunch that out, we get 41.13. So So 41.13 for the urban reading people. For the expected frequency of the first row and the second column, it would be the row sum for that entry of 42, and that corresponds to 123 again, times the column sum, now that's 108, divided by the total, 317, and that gives 41.91. So let me fill that in. So for the cell which 38 occupies, the row sum 123 again, times the column sum 103, over the total 317, that gives 39.97. Okay, so just to finish them all up, second row, first column would be the row sum. Now that's the, so we're looking at the 63. The row sum is 194 times the column sum 106 over that total, and that crunches down to give 64.87. Okay, second row, second column. Let me fill that one in. Okay, second row, second column. Oh, I'm sorry. You didn't see some of what I was writing. So I'll give you a second to catch up if I apologize for that. So second row, second column where the 66 lies. 194 is the row sum times 108, the column sum, over the total 317 gives 66.09. And then finally, second row, third column, row sum again 194, column sum 103, divided by that total. And that gives 63.03. Okay, so that's how we find the expected frequencies. Okay, the next thing is the chi-square distribution itself. The chi-square distribution, all the values are greater than or equal to 0, so there's no negatives. And just like the t-distribution, it's a family of curves where we have degrees of freedom. The area is considered to be 1 or 100%, and they are positively skewed. So what a chi-square distribution looks like, if we draw the axes, we draw a vertical axis because we're starting at zero. This would be the value of chi-square, and it basically looks like you're going on a roller coaster. That is, you go up the hill, and then you reach the peak, and then you go down the hill. And that might be for small degrees of freedom, let's say 5. For a larger degree of freedom, it's less steep than when it reaches its maximum. It's less of a drop. And that might be degrees of freedom, let's say of 10. And then as the degrees of freedom get larger, it starts to look somewhat normal. So that would be degrees of freedom of, let's say, 25. Okay, so the way we're going to draw it is more like the first one that we drew with the degrees of freedom of 5. But it's used to test the independence of two variables. So we're going to be able to determine if one variable influences the probability of the other. And we have some conditions that you could pretty much assume are going to be true for all the situations that we're going to encounter. But the observed frequencies have to be from a random sample, and each of the expected frequencies have to be greater than or equal to 5. And the sampling distribution is approximated with the formula for degrees of freedom of r minus 1 times c minus 1, where r and c are respectively the rows and columns of that table, contingency table. And the critical values are found in table 6. First off, before we go there, if you look at the formula sheet under chapter 10, it mentions the degrees of freedom, number of rows minus 1, number of columns minus 1, their product. That's for the independence test. There's what they call a goodness of fit test. We're not concerned about that. We're only concerned about the independence test. And this is our critical value that we're going to be using. And so we have, since it's a different distribution, there's a different table. And this is table 6. And table 6, you can see they've got a sketch of what the chi-square distribution looks like. We're only going to be dealing with the right-tailed test, and it's pretty easy to discern how to use the table because there's your degrees of freedom on the left, just like the t-distribution, and the value of alpha, level of significance, in the respective columns. So we'll see that momentarily. And when we state our hypotheses, because we're going to be doing a hypothesis test, we always say that HO is that the variables are independent, and HA is that the variables are dependent. And that's because it's a test for independence, so we're assuming HO is true, that the variables are independent. And here's the formula for the chi-square test statistic. Notice it's the sum of, and then the O's minus the E's over the quantity squared over the E's, where O and E are observed and expected, respectively. And here's a note about our assumption that the two variables are independent. So we assume the null is true as always. And if there's a small difference between the observed and the expected, then the chi-square test statistic will be small. So if there's little differences between the O's and the E's, and the null hypothesis is not likely to be rejected. But the larger the differences between the observed and the expected, the larger chi-square is going to be. So larger differences or larger discrepancies, larger chi-square is going to be, and more than likely the null hypothesis is more likely to be rejected. Okay, so moving on. We have another note here about the chi-square values are always going to be positive or 0, and therefore it's always going to be a right-tailed test. So there's a couple examples finding the critical values. So we draw a distribution. First off, you might want to calculate the degrees of freedom. Remember, this stands for R by C, 4 rows, 3 columns, and the degrees of freedom R minus 1 times C minus 1. So for this case, 4 minus 1 times 3 minus 1, so 3 times 2, or 6. We would draw the distribution. Okay, and it's going to again look like a roller coaster. And it's always a right-tailed test. So this is our chi-square sub-zero critical value. And so using the table, we just simply look up 0.10 for alpha. So notice in the table, alpha is the entire area in that tail. So we look for the 0.10 column, and degrees of freedom were 6, so it looks like 10.645. Okay, so the same idea here. Degrees of freedom would be now 3 minus 1 times 2 minus 1, so that's 2 times 1, or 2. It's always a right-tailed test again. Try your little roller coaster. Identify the right tail. Shade in the rejection region. Here's chi-squared sub-zero again, the critical value, using the table. Now we're looking for alpha's 0.05. So that's the 4th column from the right. And degrees of freedom are only 2 here, so 5.991. Okay, so easy enough to do that. And now the chi-square critical test statistic. So to calculate this, the chi-square test statistic formula is the big summation of the O's minus the E's quantity squared over the E's. So you could do this in a variety of ways, but I'm going to use a tabular fashion where, okay, we're told here that the expected values are given in parentheses. So what I'm going to do is I'm going to set up a table, and I'm going to build this formula. So I'm going to have the observed and the expected in my table. So 43, 41.13 for the first cell. Okay, I'll just move across. 42 for math urban. 41.19, excuse me, 91, the expected. Math urban science people, 38. And 39.97 for the expected. Okay, now the second row, reading, suburban, 63, 64.87. Suburban math, 66 observed, 66.09 expected. And finally, for the science suburban people, 65 and 63.03 for the expected. Alright, so now let's build the formula. first thing we're going to do is take the difference between the O minus the E's, so that'll be one column. Then we'll square them. So whatever that result is, we'll square it. And then finally we'll take that result, O minus E quantity squared, and divide by E. And then when we sum this final column, that's going to be the sum of those types of things, the O minus the E squared over the E, and that'll be our chi-square test statistic. Now, you don't really need to write down the numbers. You could, but you could actually do this all on your calculator. I'll show you both ways for a few of these. But for example, you take 43 minus 41.13, and we get 1.87. Now that value is already on my calculator, so I'm just going to hit x squared and square it. So let's show this as we go. So I take 43 minus 41.13, and I get the 1.87. Now, there's no need to clear that or anything. Just hit the x squared key. And then equals, and that's 3.4969. But there's really no need to write that down, because our goal is this last column. And that result's already on my calculator. So now I'm just dividing that by E, the 41.13. And that gives me 0.0850. I'll leave it at that. And you want to take it out to at least 3 or 4 decimal places in the intermediate calculations. Okay, so now for the 42 minus the 41.91, press equals, we get 0.09. And we square that, so I hit x squared equals 0.0081. But again, really not necessary to write that down, because all I'm doing is dividing that result by the E, which is 41.91, and we get 0.00019. So 0.00, I'll call it 02, just round that. So we'll do it one more time literally. 38 minus 39.97 equals negative 1.97. Hit the x squared key, enter, 3.8809. And then we're dividing that by the E, which is the 39.97. And then we get 0.097. We'll round it to 4 decimal places, 0971. But I'm just going to put some ellipses in here, indicating that you can basically just skip that, because watch, if, as we've done, it takes 63, oops, clear that, 63 minus 64.87, press equals, then I square it, and then divide by the E, which was the 64.87, and that gives 0.0539. So if you want to write these numbers down in the middle columns, that's fine, but really not necessary. And you could double check the rest of these. 0.0001 rounded, and then 0.0616. Right, and then if we add all those together, we get 0.2979, and that's our chi-square test statistic. Because that is, here, let me I'm going to be more formal here. That's the sum of, that column again is labeled as O minus E quantity squared over E. So the sum of those things, which is by definition our chi-square test statistic. Okay, so now we'll put everything together and we'll look at a hypothesis testing problem. It's the same 5-step procedure as before, but different critical value and test statistic, and the hypotheses are always, as we said, HO independent, HA dependent, but the decision and the conclusion are the same. So it's the same critical value method that we used in previous sections as we noted there. Okay, so here's an full-blown example. We took a little bit of the legwork out of this, where we already calculated the expected frequencies. So when you do your work in my math lab, that was probably the first thing you're going to have to do. But after you get the expected frequencies, we put them in parentheses here, then you could start the hypothesis testing procedure. So the first step, HO and HA. Get a sense of what the scenario is. Got 230 math students, gender and study hours. Test the claim that the number of study hours is dependent on gender. So remember the HO, so if it's dependent, that's going to go with HA because HO is independent. So study hours is dependent on gender, going with A again. That's their claim. And HO again is independent. So study hours is independent of gender. Okay, so the second step is our critical value. We get the degrees of freedom, which again is rows minus R minus 1, C minus 1, where R is the number of rows. Okay, notice that there's 2 rows, 3 columns. So 2 minus 1 times 3 minus 1. So that's 1 times 2, or 2 is our degrees of freedom. Our value of alpha is given up here to be 0.01. And remember, it's always a rate-tailed test. Okay, so I'll draw the distribution off to the side here. We're always starting at 0. Got a little roller coaster going on. And it's always a rate-tailed test. And that's our chi-square sub-0 critical value. So we look up table 6. And it's easy enough to use, as we saw. Degrees of freedom of 2, alpha is 0.01, the second column from the right. Looks like 9.210. Okay, so then our chi-square test statistic. Okay, so remember the formula once again. Chi-squared is the sum of the O minus E's quantity squared over the E's. Some people don't build the table and they just do it by calculation of each one of these values and add them up as you go, but I think the table works nicely. just build the columns easily, and then everything's right there in front of you. Okay, so I'll fill in the first two while we can see them. 26 for the observed, 23.58 for the expected, 58 for the observed, 55.03 for the expected. Next one, 29 and 34.39. Okay, now I'll just finish copying them down. 22 and 24.42, 54, 56.97, and finally 41 and 35.61. Alright, so to build the formula, first the difference, O minus E, square those results, and then divide those results by E. So showing it literally one more time. 26 minus 23.58 is 2.42. Square it. Get 5.8564. And divide that by E, which is 23.58. And we get 2484 when rounded to 4 decimal places. Okay, I'll just show the next one, and then we'll just fill the rest of them in. So again, really don't need to show these two columns here, the O minus E and the O minus E quantity squared. But I'll show one more of them. 58 minus 55.03, 2.97, square it, 8.8209, and then divide that result by E, which was 55.03, 1603 when rounded. Okay, so once again, you can fill these in if you like. I'm just going to fill in the results, double check my work. For the third one, we get 0.8448. Next one, 0.2398. Then 0.1548, and finally 0.8158. Okay, and then if we sum that column, we get 2.4639, and that again is the sum of the O minus E quantity squared over E, which is our chi-square test statistic. So then comes the decision, and we place that. Remember, this is a 0 here, so the 2.4 doesn't have to be to scale, but it's definitely well before the 9.2. So this was the test statistic of 2.4639. Obviously, it's in the non-rejection region, because the tail is the rejection region. So we failed to reject HO, and then you could use your table, I'll remind you of that. But HA was the claim that they were dependent. We're failing to reject HO, so that means the claim is probably not true, because HO, we can't get rid of it. So the claim's probably not true. Remember, when HA is the claim, the word support is in the answer. Since it's probably not true, we could say there is not enough evidence to support the claim. And then you could finish it up, of course, by saying that study hours is dependent on gender. So the table I was talking about was our famous cheat sheet. Remember, there's a summary on the side here telling you if the claim, how to rate your conclusion. If the claim is HA and we're failing to reject HO, this is our conclusion. There's not enough evidence to support the claim. Okay, so that's the end of 10.2, and we just have 2 more quick sections left, and that'll be the end of the course. So we'll see you when you are ready.